This is a last in a short series of slides to assist paraglider and hang glider pilots in using Skew T meteorological graphs. In this section, we present a few Skew T graphics to review and to think about. You might need to pause the video from time to time to study the images in detail. Let's start by visiting the Cauca Valley in Colombia, where many European pilots travel in the winter months. You right-click on the windy desktop screen to select the soundings. Then you can use the time slider, which displays the local time, to move left and right and see how the Skew T changes during the day. Having selected the time you might want, you then go to the soundings graphic and use the expansion arrows so that you can get more detail on the same screen. In floating your cursor on the windy desktop screen, some lines are generated automatically. There's the saturation mixing ratio line going down to the left, there's the dry adiabatic lapse rate going down to the right, and going upwards is the saturated adiabatic lapse rate. You can use this to select the exact points that you want. In positioning these lines at the dew point at launch and the temperatures that might be reached at takeoff, we can see that cloud base is going to be in the region of 2,400 meters, and the temperature at cloud base is going to be about 14 degrees C. We can also see that winds are very light, and it gives you the wind direction too, although we can't quite see it on this screen recording. Let's travel to another popular winter destination, Governador Valadares. If we right-click on the site, we can open our soundings, and we can see immediately this is not a very promising Skew T. We've got a lot of low cloud. We've got some very high cloud as well, where those two lines come close together. We can move the time around to check different times of the day. We can see that the wind is coming from the east, light winds, but quite a lot of high cloud around. Let's now travel to Porterville in South Africa. We can see on the opening screen that winds are from the south-west. If we open our soundings graphic at the launch just near Porterville, we can see immediately that the environmental temperature line and the dew point line are wide apart. This is going to be a blue day. If we move things around, we can then open our soundings to find out a little bit more. We can see there's a kink in that environmental temperature line, which is going to stop the climbs around about probably 1,700 meters or so. As before, we can use our cursor to get some key data from this screen. The environmental temperature line is parallel to the dry adiabat, so thermals will be smooth and consistent, but they'll stop when the atmosphere becomes more stable. We can move our cursor back down to find the temperature at which that climb stops. It's about 19 degrees C, at which point the dew point is 10 degrees C. That large difference means there'll be blue skies and no cumulus developing at the top of the climbs. We can see also on the left-hand side the height of that climb marked around 1,700 meters. The convective temperature is around about 30 degrees centigrade, although we're launching much higher than that, so the temperature at launch doesn't need to be that high. Finally, using windy, let's go to Manila in Australia. Here again we can see the winds are coming from the southeast this time. We're going to switch models to use the GFS model here and open the soundings on the windy graphic. Our immediate impression, this doesn't look like a good sounding. The environmental temperature does decline, not terribly fast, but it doesn't look like a flying day. And on a map we can see rain coming in from the east in any case. So let's change and look at the next day, move from Friday to Saturday. And this is looking more interesting. We've got our waste creeping in again on this graphic. And if we adjust the time to midday, We can open this sounding and have a look at this sounding in a little bit more detail. The takeoff in Manila is around about 850 meters, which is a little over 900 millibars, so we don't need to worry about the strange shapes below that height. And we can move our cursor around to get those lines generated that we want. Again, we see there's no chance of any condensation. The dew point's not that relevant. Climbs are going to be parallel to the adiabatic lapse rate, so fairly even and smooth, reaching a height around about 1300 meters or so. At that height, the temperature will be about 7 degrees C, with dew point right down at -3, and the winds will be 19 miles an hour around 300 degrees. We'll now turn to the specialised set of Skew Ts that are made available to pilots in central Spain. We have 3 differing days from 3 different launch sites available to study. In this case, launch is at 1,081 meters. Note the wind direction and strength at launch on this day. What will the sky look like? And is this a day where we should worry about storms? In fact, this is a blue day with good thermals and a low chance of storms. The wind direction at launch is around 10 kilometers per hour from the northwest. The temperature forecast at launch for this day is predicted to reach 21.8 degrees centigrade. Because this temperature is higher than the temperature of the surrounding air, air parcels that reach this temperature become less dense than the air around them and begin to rise. At ground level, the dew point temperature is much lower, around 4 degrees centigrade, than the air temperature. So we are dealing with dry air that follows the standard dry adiabatic lapse rate. This ascent is marked as a black line in the graphic, while the environmental temperature sounding line is its usual red colour. At 3,045 meters, the black line and the red curve intersect. So at this altitude, the air parcel that had been heated on the ground and then ascended is now at the same temperature as the air around it, and it stops rising. The dew point temperature of the air parcel at ground level was around 4 degrees centigrade. As the air parcel rose, it didn't mix with another air mass, so the dew point temperature will have decreased according to the saturation mixing ratio lines. Specifically, at 3,000 meters, the roof of the thermal, the dew point temperature is still around 5 degrees lower than the environmental air temperature, so there'll be no condensation and no cloud will be formed. Here is a Skew T from another day and another launch site in central Spain. This time the launch is at just over 1,500 meters. The graphic highlights the convective temperature, but what winds can we expect? What will the sky look like? How concerned should we be about thunderstorms? This version of the Skew T graphic clearly highlights the required convective temperature, and in this case it's a little over 14 degrees centigrade. This is the temperature slightly above the surrounding environmental sounding at launch altitude that's required to cause an air parcel to rise. The dew point temperature at launch height is around 5 degrees centigrade. So the air mass cools at the standard dry adiabatic lapse rate of 10 degrees per 1,000 meters. As the warm air parcel rises, its dew point temperature also falls according to the saturation mixing ratio. The dew point temperature equals the dry adiabat lapse rate at 2,643 meters. At this point, the moisture contained within the air parcel condenses, forming a cumulus cloud. From that point on, the air mass stops following the dry adiabat and begins to cool according to the standard saturated adiabatic lapse rate. When the air parcel equals its temperature with the surrounding air, it stops rising. In this example, this happens slightly above 3,000 meters. The environmental air temperature immediately above this altitude is warmer than the air parcel, as shown by the blue bulge labelled CIN. This is the area of convective inhibition. The blue area is all the energy that the air parcel would need to overcome if it were to continue ascending. Note that the larger the blue area, the lower the probability of a thunderstorm. The cloud column to the right of the Skew T graphic in this case confirms this interpretation. From the point where the dew point and the dry adiabat intersect to the intersection of the saturated adiabat with the environmental temperature soundings trace is the extent of any convective cumulus. At the same time, the section in which the dew point temperature line and the environmental temperature line soundings overlap is the region in which condensation occurs, although without that being the result of any convective condensation. A final example of a day in central Spain involves a northeasterly launch site at an altitude of 1,112 meters. What temperature must launch reach for convection to occur? What wind strengths can we expect, and to what height might we expect to climb? What clouds might we see later in the day, and how much sun can we expect? On this day, we can see that winds are slightly north of east and at strengths of up to 20 kilometers an hour. The temperature at which we can expect convection is just over 20 degrees centigrade. Looking at the two soundings lines, we can see that they lie within a few degrees of each other at 4,000 meters and overlap between 2,500 meters and 3,000 meters. At these heights, we can expect cloud which may limit the sun on the ground. Any thermals formed will ascend to 2,319 meters, and the environmental temperature line is parallel with the dry adiabat all the way to this height. This is the point where condensation occurs and cumulus are formed. In this case, when the cloud begins, there is no blue bulge of stable air to prevent further convection, so the parcel of air keeps on rising. The air parcel doesn't match the temperature of the surroundings until a height in excess of 8,000 meters. So 6 kilometers thick cumulus clouds may develop. We don't want to be flying in one of those. The temperature difference between the air parcel and the real atmosphere is the extra energy the air mass holds that allows it to continue ascending. It's known as the potential energy available for convection, and the acronym used for this is CAPE. The larger the shaded red area, the higher the value of CAPE and the greater the risk of thunderstorm. Being able to predict the exact location where any storm will develop is difficult, but this Skew T curve tells us at a glance that the atmosphere is unstable and that if a storm doesn't form right above us, it may form 5 or 10 kilometers away. Many of the next Skew T graphics are stills taken from Sean Staines' excellent video presentation, which can be found on the Thames Valley web pages in their learning section. These slides help us become familiar with Skew T or soundings generated by RASP. This soundings graphic was developed for 1 p.m. on the 24th of June 2020 at Nottingham. At what height do you estimate cloud base might be? How consistent will your climbs be towards cloud base? What is the risk of thunderstorms? And is the wind strength of any concern? Can you spot any downside in this Skew T? The downside that Sean highlights in this image of the Nottingham sounding is the presence of high cirrostratus, which might damp down the strength of the sun and the capacity for it to heat the ground. Despite this, the convective temperature is only around 25 degrees, and the RASP graphic illustrates the course of any thermals using the dashed pink line displayed in this image. This line changes angle at the height where the dew point and the environmental soundings coincide. It then travels according to the saturated adiabatic lapse rate trajectory. The environmental temperature soundings line is parallel to the course of the dashed pink line, and this means that we can expect our thermals to be smooth and consistent all the way to cloud base. The height of cloud base is estimated to be around 4,000 feet. Winds are from the southwest and of strength of up to 18 knots as indicated by the green wind strength line. The Cape number included at the top of the RASP soundings is only in double figures. We only need to become concerned when that number is greater than around 500. This is a second example generated on Tuesday, July the 7th for 1 p.m. in the afternoon. What concerns might you have regarding this day? Is it looking like a good flying day? More specifically, what direction is the wind, and how thermic is the day likely to be? Will any cumulus overdevelop and shut down further convection? What is the risk of overdevelopment? In this example, there is no high clouds likely, but the two lines are within 2 or 3 degrees of each other at around 4,500 feet, and the pink dashed line is illustrating that convection is likely to generate thermal activity. The skew shows the classic hourglass or egg timer shape that should by now be spiking your interest. Wind is around 12 knots and is coming from the north-northwest. At an altitude of around 3,800 feet, the environmental temperature line and the dew point lines are sufficiently close together for condensation to occur, and this is cloud base. At this point, any rising air will change its rate of cooling and follow the saturated adiabatic lapse rate trajectory. Condensed water within the air parcel continues to rise until it meets the environmental temperature line, which is briefly following an isothermic course. This inhibits further convection and caps off the further development of clouds at around 4,500 feet. Because the air is now very dry, the dew point of the air has fallen to -10 or lower, and this wide gap between the dew point temperature and the environmental temperature above the cloud is a good indicator that cloud spread out is unlikely to be a problem. The day should continue to work well. The Cape figure in the line of text at the top of the soundings output is also only 42, and this signifies a very low risk of thunderstorms. Finally, we have one more RASP sounding for Fairford, generated in August 2011 at 10 a.m. What cloud can we expect at this time, and how good is this day looking? In this sounding, there is a lot of high cloud around and some non-convective cloud at around 5,000 feet. Any convection that occurs will be capped by a more stable air mass at around 3,000 feet, and because the environmental air is progressively becoming more stable until it meets the dew point temperature, we may find that the top of the climbs will become a little slow, broken, and perhaps a little rough. Only stronger climbs will reach the level of cloud. Bear in mind that these comments only apply to this Skew T, and it would be wise to generate another graphic for later in the day. The next few examples are taken from Kelly Farina's Mastering Paragliding Facebook feed. The base soundings graphic is generated from the subscription Meteor Blue Met service. The images of the Skew T graphs that he uses each day for flight planning and analysis include his own notations. I can't pretend to understand them all, but he consistently highlights the ground temperature he expects, the dew point temperature, and the air temperature he anticipates at cloud base. This is a good example of circumstances where the normal stable layer that caps cloud development is missing, and the environmental temperature soundings line lies a long way to the left of the saturated adiabatic lapse rate trajectory that an air parcel will follow once it's met the saturation mixing ratio line that has been established by the surface dew point temperature. This can lead to towering cloud development and a high risk of thunderstorms. Note that Kelly also has concerns about wind and highlights the fact that the environmental temperature curve below cloud base starts to move towards the right with altitude, and the air beneath the cloud becomes more stable. Kelly is keen to highlight that in his experience, these conditions tend to lead to bumpier conditions at the top of our climbs, as the rising air's inertia starts to exceed the lifting forces generated by the difference in air temperature and its density. In this example, there is little evidence of the classic hourglass that we like to see these two soundings lines describe. Because the dew point temperature line doesn't move to the left after the altitude at which the thermal height is predicted to top out, Kelly considers that any clouds formed will be flat and that spread out is likely. The dew point line looks a considerable distance away from the environmental temperature line in this image, but do take note that the temperature scale at the foot of the image suggests that the two lines are actually within 2 or 3 degrees of each other. This is certainly close enough for condensation to take place. Here's a RASP sounding taken from the day in which Tim Pentreath did 140 odd K from Malvern. We've got westerly winds. We've got a cloud base of 4,500 feet. We've got no sign of any high cloud. We've got the classic hourglass shaped sounding. This is another of Tim's fantastic flights, this time in southeast Wales. We can see that wind strengths were around about 10 knots from the southeast, varying a little with altitude as is normal. The convective temperature is probably about 28 degrees centigrade, and we've got a very high cloud base this time, probably around about 7,000 or even 8,000 feet. Pretty much a blue day. Those two lines aren't close enough together, but they are quite close at very high altitudes in excess of 30,000 feet, so there may have been some high cirrus around. On this day in May, we can see that there was quite a cloud bank at around about 5,000 feet, and further high cloud as well, around about 26,000 feet. Wasn't the greatest day by the looks of things, quite deep cloud, westerly winds, relatively strong that day. And that concludes this series on the Skew T, also known as the tephigram or soundings.